All right, we are at the point now in the semester or this lecture series where we finally have all of the pieces. We have the kind of how the immune system works to look at different ways that the immune system plays a role in preservation of the body. And in chapter 11, this is going to be focusing on the development of memory. And so we're going to look at the secondary immune response. And then we're going to take some time to see how, as humans, we've harnessed the power of immune memory to come up with some pretty important technological, healthcare advances. So in this chapter, let's get to the next slide here. We're going to start out by reviewing a little bit about that primary immune response. Up to this point, we've really just been focusing on what happens during the first time somebody is exposed to a certain pathogen. And so that's called the primary immune response. And through that, there's really two goals that are achieved. If the person survives this infection, they're going to develop a very powerful force of effector cells, B cells, T cells, a variety of different types of T cells, and then the molecules that come from those cells to clear the infection as quickly as possible. And then the second thing that comes about, which is the focus of this chapter, is the development of memory of that pathogen or of that certain strain, that foreign invader. And it's the building up of these memory cells that sticks around and waits for any other time the body is exposed to it. And so this reserve of memory cells then is ready and waiting and will go ahead and attack very early on in what we call the secondary immune response. So that's the focus then of chapter 11. And in the secondary immune response, we're going to see that it's way faster, it's way more powerful from the get-go, and the infection is cleared before hopefully you even realize that you've been infected with that pathogen. So there really are two parts then to this chapter. The first part is going to focus on the development of memory. So how it is developed, and then what that secondary immune response looks like because of those memory cells. And then the second part will look at immunizations. And so how memory can be used to develop a vaccination to give what we'll call artificial exposure. So we're going to break it up into that part or in those two parts. And so we're going to start out then looking at how memory is developed. So there's a few terms that I want to bring up. One is protective immunity. And so this table or this chart down here on the bottom has a lot in it. And I'm going to have it on the variety or different components of this table or this chart on the next few slides. And I'll have identified where we're at looking. So you can see right now we're going to start with this area called protective immunity. So up to this point of the semester or this lecture series, whichever one you're utilizing, we've really been spending all of our time looking at the components of the immune system, how they work together, how they develop to fight off a foreign invader the first time the body is exposed to it, and that's the primary immune response. So we have this first infection that occurs, and it takes quite some time, right? We have the innate immune system that kicks off right away, but then if the innate immune system is overrun, the adaptive immune system will kick in, but it can take a week, it can take 10 days, it can take 2 weeks before that infection is actually cleared. And so we have two graphs here. One is the number of effector T cells, and then we have the titer of antibody. And right away, it takes a long time, but then it really grows and it gets a high amount, and then it's going to start to wane. But as it decreases, there is this point where there's still protection, but it's going to be by antibody alone. And we call that protective immunity because even though the first immune response has been terminated, there's still a decent titer of antibody that hangs around in the system. These proteins don't degrade immediately after an infection. And so they're going to be present in the blood, they'll be present in the lymph, they'll be present in the tissues, on the mucosal surfaces, wherever this antibody is. And it's there so that if you get infected, again, during a short time after. So a great example of this is like when there is something going around, right? You might catch whatever respiratory virus is going on and you get this cold, but then you're pretty good for, a few months because you're not going to get that cold again, that cold virus again. Well, even if you do get it, that protective immunity should cover it. And that antibody should neutralize those viruses when you come into contact with them again. So it's there, it's going to stop and neutralize that pathogen from ever getting in. And so pretty much they're immediately neutralized. You're not going to get the same cold twice if it's the same virus. And if it's a bacterial infection, that antibody is going to serve as a neutralizer, but also an opsonizer. And so it will opsonize that bacteria, and phagocytes will take it up right away. And so you won't end up getting sick again from that. And so during that time, because they're picked up so quickly by these protective antibodies, they're not going to have time to grow and replicate and affect other cells. And so it is a really protective state where you, as long as it's the exact same pathogen and it's a shorter period of time, you're not going to get sick again, which is really kind of nice, right? Now, the amount of circulating antibody that is pathogen specific, though, will decrease over time. Those plasma cells are not going to continually make antibody against everything we've ever been exposed to at high levels. It's only going to make antibody as it's needed. And so as those antibodies break down, as those plasma cells start to shut down production of that pathogen-specific antibody, the titers are going to drop. We call it an antibody titer. The higher the titer, the more antibody you have per milliliter or per microliter of plasma. And so it's a short amount of time where you have a high antibody titer, but then it's going to eventually drop as the number of plasma cells producing that antibody drops. It doesn't usually fall to zero, though. There's always going to be some baseline of cells that maintain a production of those antibodies. It could be low, though. You end up with a pretty low titer, but they're very long-lived plasma cells, and usually they're going to be hanging out in the bone marrow. They just are self-replicating. They'll continue to live for potentially your entire life in the bone marrow, and they are able to be called up quickly if ever exposed to that same pathogen at any point in your life. So think about like measles, for example. You were vaccinated with an MMR before you even knew, right? As a baby, you got your first dose of a measles vaccination, and you have those long-lived measles-specific plasma cells living in your body. So even if you're 75 years old and you get exposed to measles, those memory cells can be there to produce antibody and neutralize the measles virus before it can actually cause infection. Pretty awesome. Now, these long-lived plasma cells are only about half of the long-lived immunity you have. So they're going to hang out, they're going to live, but there's also another component to memory, which makes up about the other half, and those are called memory cells. And we can have memory B cells, and we can have memory T cells. And these memory B cells and T cells are long-lived as well, but they're not doing anything. They're kind of dormant until they get activated again by pathogen. And so the long-lived plasma cells will continue to produce a low-level baseline amount of antibody, but the memory B and T cells have their T cell and B cell receptors on their surface, and they're already high affinity. And in the case of B cells, they're going to be isotype switched to IgE, IgA, IgE, for example, and so they're ready, they're waiting, but they're not doing anything until they are activated again. So let's talk about when they get activated again. And that is the second part then of, well, maybe it's the third part, depends on how you look at that graph, where we have our second infection. Now, please know that we say second infection, but this might be the second infection. It might be the third. It might be the eighth. It doesn't matter. Any subsequent infection after that first infection is considered a secondary infection. Well, a second infection. Secondary infections tend to be, that term tends to be saved for something else. Okay, so the first goal again of the primary immune response is to stop the infection and clear the pathogen that has outran the innate immune responses. We've looked at this in depth. We know that it includes the development of a clonal population of T cells. Those T cells differentiate into a variety of different effector T cells based on the type of pathogen. And we know that it creates a clonal expansion of antigen-specific B cells that make plasma cells that make antibody. And these effector B cells and T cells work together very rapidly for those few weeks it takes to completely clear that first primary infection. Now, the second goal then is to take some of those effector B cells and effector T cells, make them differentiate into memory B cells and memory T cells, so that once they are infected or activated again, we don't have that long lag time. Look at the difference in time between the secondary infection and our rapid increase of T cells and antibody. It's almost no time at all. Where we saw in the first infection, there was a lag time, 1 week, 10 days, 2 weeks, somewhere in there, before we could get to high titers of antibody. And actually, the antibody titers and effector T cell titers in the secondary infection, or not secondary infection, second infection, let's say, are going to be higher, stronger, better, faster, and really effective at wiping out the pathogen. So the secondary immune response occurs when a pathogen that has already successfully infected a person once gets in a second time, or third, or eighth, whatever it might be. But it's cleared so rapidly, so quickly, that the individual likely will not even know that they have been infected by that same pathogen again, because there is that rapid increase of antibody and rapid increase of effector T cells to wipe out that pathogen in the same manner that we saw in the primary immune response, but in such a fast fashion, and there's not the need for getting better, stronger antibody because it's already been switched. So let's take a peek at that quick. Primary B cell response. So the first time that the body was exposed, the B cells were naive. They were mature. They had gone through their development. They had gone through positive selection, negative selection. They had a B cell receptor, IgM, it was good. And they became activated, and they produced, to begin with, low affinity IgM. Not optimal, but it was, better than nothing. Then that B cell had to go through some processes. It had to go through somatic hypermutation to create a better antigen receptor with higher affinity. And it had to go through affinity maturation, where the clonal deletions occurred for those that did not create as strong or high affinity isotypes, or antibody specificity, or rather, I guess we could say, those clones that made the highest affinity antigen receptor were selected for expansion. And then isotype switching occurred. So T follicular helper cells told B cells, okay, here's a signal, switch to IgG, switch to IgA, potentially IgE, depending on the type of pathogen. And so it took some time for that to happen. And the affinity of antibody increased across that timeline. those heavy chains, those light chains, variable regions were able to change ever so slightly. And then the ones that made the best were selected for. Well, those were the clones that survived memory B cells. That means that memory B cells are going to have B cell receptors that have the highest affinity antibody and the highest affinity B cell receptors once they become a memory B cell. And so that timeline gets shortened then for any second exposure, because we don't have to go through, the B cells don't have to go through that affinity maturation, hypermutation, isotype switching. It's already been done, and the memory cells are ready for that. So, but okay, so this slide is kind of a more confusing concept, or maybe a little bit deeper concept, where yes, we have memory B cells ready to go on a second infection or any subsequent infection. But that doesn't mean that there aren't naive B cells out there that will also recognize this pathogen. To prevent the body from wasting time and trying to start a whole new primary immune response, there is this system that the immune system has, where any pathogen that is coated with high affinity IgG, which will be out there because of the memory cells, when a B cell, a naive B cell, wanting to be activated, finds this pathogen, and they're like all excited because they found their antigen. Oh, but somebody's already been there. Oh no, there's already high affinity IgG coating this thing. That B cell, rather than being stimulated to go on and start the whole thing again for a primary immune response, that B cell actually gets kind of just shut down. And it gets a negative signal through its B cell receptor, and it is induced to die by apoptosis. And so that's preventing another primary immune response from starting when we already have a memory response that can take care of it. So rather than waste energy on starting over again, let's just use the memory response and call it good. And so that secondary response then can be very quick. That memory B cell is activated, and it's going to then immediately put out high affinity IgG or antibody that can coat the pathogen. This is really great for preventing excess work or wasted work. There is a downside, though, to this, and that is best described through the example with influenza. So the suppression of naive B cell activation during a secondary immune response is really great for those pathogens that don't ever really change their epitopes. Measles, for example. Measles is measles, and it looks the same so far throughout our lives, right? Influenza, though, is an RNA virus, and RNA viruses tend to mutate quite rapidly and change their external epitopes. And so from season to season, influenza viruses can look slightly different on the external surfaces, and so to our immune system. So when B cells then are shut down because they might recognize that, oh, there's already high affinity antibody attached, we won't ever get a response to a new strain. So here is a chart that shows how from year to year, the external surfaces of influenza epitopes can change. And the first year we can either be infected naturally by getting influenza, or we get the influenza vaccine and we build memory against it. Either way, it's going to work. And when the next year, that influenza virus looks kind of the same, but slightly different because there's a slight mutation. And rather than building a new high, potent antibody against the new strain, it's actually those B cells are shut down because there's like, oh, and wait, there's already high affinity IgG on there. We're okay. Now you might not get infected, or you might not, have a true infection then, because maybe those antibodies can work that first year. But after the third year or the fourth year, pretty much you're not having any antibody response at all, because the memory antibody isn't really that great anymore, but it's good enough to shut down a new response. And so for those pathogens that frequently change their surface epitopes, this can be an issue. This shutting down by the memory can be an issue. So that's why, in the case of influenza, new vaccines are needed every year. That's why in the case of like some of the other childhood pathogens, you can get multiple infections throughout your life, even though you've had it before. Strep is a great example. So although really great to not waste energy, for some pathogens, it's not the most effective use. Now, just like B cells, T cells also have memory cells, but there could be naive T cells out there that want to start a primary immune response, right? And this can lead then to a clone of memory T cells that have improved capacity for attachment to a pathogen. The population of memory T cells then should mirror the population of pathogen-specific effector cells that contribute to that primary immune response. This means that memory T cells are going to include CD8 positive T cells. There's also going to be memory T cells of all the different effector helper cells. So helper 1, helper 2, helper 17. They can all be activated directly at the site of infection by a dendritic cell, and macrophages presenting their still has the ability to present to a naive T cell, but it's not to a naive T cell, to a T cell, an activated response, but it's going to be the secondary response rather than that primary immune response. We talked about how dendritic cells really are the only cell that are able to activate a naive T cell. This is where macrophages, as a professional antigen presenting cell, can also activate T cells, but it's going to be the memory version in that second immune response. This also decreases the need for the co-stimulatory molecule to have to also bind. Now, there are memory T follicular helper cells as well, but they're retained in that secondary lymphoid tissue. And just like with a naive, or with I guess not naive, but a first time around T follicular helper cell, memory T follicular helper cells are also going to help antigen-specific B cells make antibody. So same types of roles that they had in the primary immune response. It's just that they're going to be ready, waiting, and there doesn't have to be that co-stimulatory molecule to get things going. Memory. Here's a summary slide that contrasts the primary immune response to the secondary, or against the secondary immune response. And side by side, you can see that they're pretty much just, there's similarities definitely in like the effects that they have and the jobs that the cells have, but they're very different in like the amount of pathogen. Primary immune response only takes a small amount, or a small number of pathogen cells are actually activated to get this clonal expansion. But then in the secondary immune response, there's already this clonal expansion of cells that are ready to fight the pathogen. So a much more powerful force from the get-go. Primary immune response takes longer to get going than the secondary immune response. Primary immune response starts with IgM, where the secondary immune response doesn't even waste its time on IgM and really just starts putting out IgG, IgA, maybe IgE, depending on the pathogen. High threshold for activation. B7 has to bind to CD28. There has to be co-stimulatory molecule sent, multiple signals. Not so much for the secondary immune response. Those memory cells are ready to go. Delay, yep, we've talked about how it takes a little bit more time, and those T cells need to be activated and then move to the tissues in the primary immune response. Memory, they're already there, they're waiting, they're activated right in the infected tissue. Now, the innate immune system works only by itself until it's overrun and the primary immune response kicks in. The activated or the adaptive, where in the memory response, there actually is the innate and the adaptive running side by side from the get-go, because the innate is going to go on regardless. Innate is just there. It's non-specific. It's non-self versus, finding non-self and trying to get rid of it. But with the memory, it's going to kick in right away. And so you have both of them running in conjunction with each other. So very exciting. And I'm really looking forward to when in the second part of this lecture, I'm able to talk about how we've been able to use this memory to make a really great healthcare advancement.